Buongiorno a tutti. This is the end of my Italian, unfortunately. I'm going to talk about science and technology, theoretical and historical relations, and you find the Italian translation below. Now, the point seems to be that the relationship between science and technology seems very simple, and we all probably have some idea of it, namely, technology is based on science. It exploits scientific knowledge for technological purposes. So if you ask people on the street, why does the government pay for studies in physics and chemistry and biology? It's probably because we need these sciences for technological applications, and technological applications we need for the economy, and therefore it's good to have science at the universities funded by the government. Now, in fact, the relation is not that simple. It's not wrong, really, but it's more complicated, and there are at least two reasons for more complications, and I'm going through these complications in the course of the lecture. First, historically, for a very long time, in fact, up to the mid-19th century, technological development was independent of science. You just have to go into the past and look, for example, at Roman technology, which flourished. I mean, many aspects of Roman technology, but also in medieval times, many technological artifacts, and they were built without the help of science because, well, in medieval times, modern science didn't exist. In Roman times, modern science didn't exist, but still there was a tradition of producing technological innovation and very sophisticated artifacts, ships, cathedrals, and whatnot. And all that was done without any science. So there must be some developments of technology which are absolutely independent of science because, as I said, modern science at that time did not exist, but that's not the end of the complications. And the further thing is, when one looks a little closely, is that ancient, that means, and medieval science, which is all based on Aristotelian philosophy and Aristotelian view of science, this ancient science was not technologically exploitable. It was just a type of science that could not be used for technological applications. I'm coming back to that issue because that's also something many people are not aware of, and it's very important to understand that. And especially with the change to modern science in the 17th century, a new form of science was discovered that was, in principle, technologically exploitable. And that's a very interesting transition, which is important to understand if we want to understand our modern times in which science indeed is technologically exploitable. So these are the historical and theoretical complications for our understanding why modern science is technologically exploitable. And the fact is even, and that will be at the end of my lecture, hopefully explicit, that modern science is necessarily technologically exploitable. So if we develop our course in history that we're following for the last 400 years by developing science, it will be necessarily leading to technological innovations. We can't have the development of science without the potential for technological innovations. There is a link between the two, which is important to understand. This is especially important. It's now not the time any longer, but some 20 or 30 years ago, people speculated about a form of science that would not be technologically exploitable because they were afraid of technological applications, but that seems to be impossible with the current form of science. I'm coming back to that. Okay. Now I'm going to tell you what the steps of the argument are, because there are certain steps there and heterogeneous steps, and in order that you have the line of the argument, I tell you now what the steps are, even if you do not understand the series of steps themselves, and I'm coming back to them and explain everyone. So the first step in the argument is that this is here only a statement which you can only hear, but you have no argument, but I will give you the argument. that modern science is technologically exploitable. That has a reason, and the reason is because modern science proceeds essentially by experiments. So there is a connection between the experimentalist methodology of modern science and the exploitability of modern science. There's a connection I'm going to explain to you. So the question is, if I want to understand why is modern science technologically exploitable, I must understand why is modern science proceeding by experiments. That's the next step. So that is the next step. And this will be modern science proceeds essentially by experiment. Science is, of course, in the sense of natural sciences. In French and Italian, it's not always clear what the equivalent terms mean, but it excludes the social sciences mainly and the humanities. So modern natural science proceeds essentially by experiment. That itself has two main reasons. Because it has a particular concept of nature, I'm going to explain to you what that is, and it has a particular epistemic ideal. I'm also going to explain what that is. And these two things in combination make experiments cognitively relevant. So in other words, it is not just trivial that experiments play a role in modern science, but it is a particular combination of two elements which were invented in the 17th century, and these elements together bring a location for experiments in the course of doing science. As I said, this is not just absolutely trivial, and we'll see that in Aristotelian science there is no place for experiment, and therefore there are no experiments in Aristotelian science. It's very important to understand why, for modern science, experiments become something that's epistemologically very useful, in fact, indispensable. Okay. And my task is then to show you the interplay between the concept of nature, I'm going to explain what that is, and the epistemic ideal, and the subsequent cognitive role of the experiment in modern science. Because these are the steps why you can understand, or how you can understand, why modern science is technologically exploitable. So there are some abstract steps. I announced them now, but I give you the details and give you each step separately in order that you understand the steps of the argument. So therefore, the content of my talk is the concept of nature of modern science. I know that you can't imagine what that may be, a concept of nature. I'm going to explain it to you. So this is one element. The second element is what I call the epistemic ideal of modern science. Again, you don't know what that is. I'm going to explain it to you. But we need these two elements in order to understand why science can play a role, why the experiment can play a role in modern science. Okay? This is the idea, and from that we then get the technological exploitability. Namely, modern science is technologically exploitable because it uses experiments. And because these concepts are very abstract to you, and we are in a sense very familiar with them, I make them visible by a contrast, namely by the contrast with Aristotelian, ancient, and medieval science, because this form of science, this old form of science, uses a different concept of nature and has a different epistemic ideal. And then you see by contrast what our current concept of nature and our current epistemic ideal is, and why that specific combination leads then to the specific use of experiments in modern science and resulting then to technological exploitability. So this is the idea. All right, I hope that in abstract the line of arguments is now clear, and therefore I start with the modern concept of nature that will lead us the way towards the end. So, what is a concept of nature? Well, a concept of nature, how we use it here, is a descriptive idea of the fundamental characteristics of nature. You're just expressing what you think nature is in principle as a subject of science. This is what I call a concept of nature. It's descriptive. You are describing what you think the fundamental characteristics of nature are. So, in the case of modern science, this is the following. You think of nature as an object of modern science, as the set of all spatio-temporal objects, I mean things that are out there. the set of all these spatiotemporal objects, independently of their origin, whoever made them, however they were generated, whatever. And the basic idea is these objects, these physical objects, they are subjected to natural laws. So natural laws is something completely self-understood for us, completely natural, trivial, but it's a new idea, and it was really only invented in the 17th century, explicitly in Descartes in a letter from 1630, a very clear conception of a natural law. A natural law is a modern idea, and it's fundamental for the modern understanding of nature. Nature is something which is governed by natural laws, which is of course familiar to all of you, but it's historically a new idea. It's not something that's absolutely natural or trivial or evident. No, it is not. It is a historical, extremely important step in our understanding of nature to conceive of nature as something that is governed by natural laws. This is, by the way, a deeply theological idea. The idea in the 17th century was our societies are governed by laws that we give them, and nature is governed by laws that God has given them. So in a sense, modern science is deeply theological. Okay, that was forgotten then in the 18th century, but in the 17th century, this was present. Okay, so what is a natural law? Again, in very abstract terms, a natural law is a universal relation. A relation meaning to bring something in between two things, and in a universal way, so such that it doesn't hold for two particular things only, but it holds for many things, all things of one particular kind. Here's an example, and I take an Italian example, of course. It's Galilei, the law of free fall. And the law of free fall, you may remember, if you don't like to remember your days in the Liceo, well, I tell you what it is. D is the distance, G is the constant of gravitation, and T is time. And you get that very simple formula. D is a half times the acceleration times time squared. So this is Galileo's law of free fall, and he found it not very far from here, as you all probably know and are very proud of. Okay, now if you want to put that in a little formula, then it is modern science, in contrast to Aristotelian science, as I show you in a minute, modern science examines nature with a view towards universal relations, namely natural laws. So when a modern scientist looks at nature, he thinks, or she thinks, because there are women also in science, not only in law, as I can see here, a scientist looks at nature looking for general relations, which are then called laws or even models or something like that, and modern science want to discover the laws that hold in nature. Now here is the contrast to the Aristotelian concept of nature, and you will see, even if you're not familiar with that at all, you will see immediately it's very different from the modern concept, because there in Aristotelian, in ancient and medieval times, nature was thought completely differently. Namely, in the sense, nature as an object of science is the set of natural objects as opposed to artifacts. Natural objects and their natural parts. So the object of science in the Aristotelian concept is only natural things, dogs, human beings, trees, but not buildings, not a thing like that, not a pointer like that, not computers. They were never the object of science in ancient times. So it's a very different distinction that's playing here, namely the distinction between artifacts and natural objects. And natural science was about natural objects and not about artifacts. It's very strange for us because we think, well, all that stuff functions the same way, whether it's in nature or whether it's technologically produced, but that was a very different idea in ancient times. And the fundamental subject then of Aristotelian natural science was then the essence of natural objects. And what one wanted to know was their natural motion and change. So natural objects have a natural motion, how they move in space, and have a natural way of changing. And if you want to understand the natural objects, then you must understand how they naturally move and change. That was the idea of Aristotelian science, and therefore the behavior of artifacts was completely irrelevant. This wasn't natural science, this was technology in ancient times. It was a complete divide between technology and the understanding of natural objects. And as the name suggests, nature, you want physis in Greek, I mean the things that grow by themselves to what they are. This is what physis is and what is in natura also. And in nature, the idea was natural science investigates these natural objects that we find out there without our intervention, and we want to understand why they are doing what they are doing, right? Changing, moving, everything. And they do that, that's the idea, out of something like an essence, that's their inner core, so to speak. It's a metaphor, whatever the essence is, but you've got to investigate the essence, and then you can understand why these things behave and change as they do. Okay? So, again, in a very short formula, Aristotelian science examines nature with a view towards universal properties, namely the essential qualities. So the natural objects have an essence defined by essential qualities, and they are then universal because all dogs have the same essence, or all trees have the same essence, and you want to investigate these essences, and once you understand the essence of a tree, then you do understand why a tree grows to his full size and then decays later. This is just in the essence of living beings that they behave like that. So you see that the focus of attention in Aristotelian science is very, very different from our idea, because the focus in Aristotelian science is on particular things, and you look at their properties. Whereas in modern science, you do not look at particular things and their properties, but you look at their relations, and the relations are natural laws. So you are interested in how things behave among each other, how they influence each other, but you're not looking at the individual thing and think it has an essence that is the focus of your attention. So you see the difference here to the relations. What is the same, of course, in Aristotelian science and in modern science is that you are interested in universal things. You are not interested in a particular thing, but you are always interested in universal things. In the Aristotelian case, universal qualities, and in the modern case, universal relations. So essences versus natural laws. So this is the concept of nature, and now that should be now more concrete in your mind. What I mean by a concept of nature is just the idea, what is it that I'm investigating? And as you see, you can conceptualize what you investigate, nature, in very different ways, which is, by the way, a very, very general property of all sciences. You somehow conceptualize your subject matter, and you make many decisions which are then influential for the rest of your activities. It's very important to see that. Okay, now the second ingredient is what I call the modern epistemic ideal. And again, I know that you do not understand immediately what I mean here. Okay, what is an epistemic ideal? An epistemic ideal is now a normative idea. Remember, the idea of nature was a descriptive idea. You describe what nature is in very general terms. And here you have a normative idea, and I don't have to explain to law students what the difference between descriptive and normative is, I guess at least. A normative idea of the fundamental characteristics of scientific knowledge. So you say, with this normative idea, what you think what scientific knowledge should be in order to be scientific knowledge. And you have to have such an idea if you start doing science. So the point in the modern epistemic ideal is this, the very important point, that the knowledge of natural laws and other relational universals is gained by means of singular empirical data. And gaining singular empirical data means you observe and make experiments, and you can only make an experiment or observe something singular, a particular case. You can never observe the general case. So when Galileo did his experiment on the inclined plane, of course he could observe only singular cases. One ball rolling down, and then he was trying to get the time, how long it took it to roll down the whole way. So you always observe singular things, but finally you're not interested in the singular things, you are interested in the laws. So the law of free fall doesn't speak about that singular particular case only, it speaks about all cases of free fall. So the problem is, how do I get to the knowledge of natural laws if I'm only able to observe singular empirical cases and experiment with them. So the idea in modern sciences, and that's a complicated step, and I'm only naming it and not describing it in more detail, that there is fundamentally a bottom-up transmission of validity from empirical data to the universals. So somehow you must make the step, you observe certain things, particular things, singular things, and then you somehow generalize to the universal things. So by many observations of free fall, then you somehow generalize in a risky step to the knowledge of the law of free fall. Okay. That must be done in modern science. And the consequence is, because that step is not a step of deductive logic, having singular observation, then to a general statement, it's not deductive, it's what the logicians call ampliative. You get more at the end of the step than you put in it, and therefore it's a risky step. And the consequence is, because in modern science the knowledge of the laws is gained in this way, scientific knowledge remains forever hypothetical. But this suffices for scientific knowledge in the modern sense. So we know that modern science, the knowledge is hypothetical, and we say, well, we cannot get more, this is just the modern situation, but I tell you, this was different in antiquity. So we can very roughly say, again, in a formula, if you want to take that home and tell your parents and your little sister what science is. So we have in modern science a hypothetical, deductive organization of knowledge, right? Hypothetical because the knowledge that you have is hypotheses about natural laws, but you can deduce from them empirical singular data. So you can call that a hypothetical, deductive organization of knowledge. This is the modern epistemic ideal, and you may say, well, isn't that obvious? Isn't that clear? Well, it may be, because we live in the 21st century and you got used to it. You went to the liceo and you know, well, this is the physics and the chemistry classes that you loved so much, and this is why you study law. And this is just what we know, but you see, if you see the contrast that I'm presenting to you now, that this is not just trivial and evident. You see that if you go back to the Aristotelian epistemic ideal, which is different. And the Aristotelian epistemic ideal is the idea of a demonstrative science, and that's in part similar to today's understanding of mathematics. So in mathematics, you have to get, for every statement that you make, you have to provide a proof. And the proof makes the knowledge that is expressed in the theorem or in the statement there, makes it absolutely certain relative to the axioms. If you know the axioms, or if you believe the axioms, then the theorems are just proof. Now, I remind you again of school days, this time concerning mathematics, but I'm not making a joke about that. Okay. In the epistemic ideal of Aristotle, this is the same as in Euclidean geometry, where the idea is that the axioms of Euclidean geometry are something like evident. You just look at them and you realize they are true. So the word evidence means evidere. It means that the truth shines out of them. It's not a subjective thing that they are evident. They aren't just evident for you. The idea is that you look at them and they shine. You just see the truth in them. So the axioms in the Aristotelian epistemic ideal are taken to be true, and they are the source of all scientific validity. So everything that's true in Aristotelian science is true due to the truth of the axioms. They are the source and the core of all validity. And that means validity is then transmitted top-down to the theorems by proof. And this is the other direction, than from modern science. In modern science, you start with the particular things, and then validity moves up towards the general laws, and this is completely, really different, 180 degrees of the Aristotelian ideal, where validity is transmitted top-down to the theorems by proofs. And that means then that scientific validity is equal to proven truth. Scientific knowledge is absolutely certain, what you know from mathematics. The idea is that scientific knowledge is absolutely certain, and you can describe that very roughly, again, with a formula. It's the categorical deductive organization of knowledge. Categorical meaning this absolute truth idea for the axioms. It's categorically valid. This is just a term from philosophy that's called categorical, and deductive because you can deduce the theorems out of the axioms. And what you see here is that the picture has changed very much in comparison to the modern ideal in the direction how validity is transmitted from axioms to truth. And also what you see is that in the Aristotelian epistemic ideal, one is not satisfied with hypothetical knowledge, but knowledge is only scientific if it has been proven to be absolutely certain. And one of the insights, of course, of the 17th century is, or in the centuries before, that unfortunately this ideal cannot be fulfilled outside of mathematics. That was a very harsh insight. Okay, so I got to tell you again, now I showed you the two concepts, namely the concept of nature and the epistemic ideal, and they stand in a certain relation. And that's absolutely important to understand that relation then, in order to see then later how the space is generated for the experiment in modern science. Now, one can put that in the following suggestive way, that the concept of nature determines what scientific questions can be asked. Because the concept of nature tells you what nature is in principle, and you say then, say in modern science, oh, nature consists of natural laws, and that means the good scientific questions are those questions who say, what is the natural law that governs this or that situation? And therefore the concept of laws brings your attention, focuses your attention to certain aspects of nature, and these are the questions then that you can ask about nature. Now, you don't want to ask the questions alone, but you want to have answers to the question, and you must determine whether a certain answer you are giving, whether that's good enough, whether it lives up to the standards that you have, and that's exactly what the epistemic ideal tells you. So the concept of nature tells you what sorts of questions am I able to ask, and the epistemic ideal tells you what sort of answers are scientifically legitimate. So in the case of ancient sciences, of course, if you make a statement, you must give a proof, right? Otherwise, it's not scientifically legitimate. In the case of modern science, a proof is not necessary. Well, unfortunately, it's not available, but you've got to make certain that you have, as one calls it, inductive arguments, arguments from experience, why you believe in a certain law, say the law of free fall. So it's this interplay between questions and answers which you can apply here, and I think it's a very useful way of getting it clear, the simple structure that's behind that. So the point is then that both the concept of nature and an epistemic ideal are presuppositions for every form of science. Every form of science presupposes that, and that holds also, by the way, for the social sciences and the humanities. You have to have an idea what the object is, and you have to have an idea what legitimate science is, and they must, of course, somehow fit together. But they are corrigible. That's very important. That's not for once and for all, as we see, because we moved from Aristotelian science to modern science, so people corrected their idea what nature is, and they changed their ideal of what good legitimate scientific knowledge is. Okay, so far so good. These are two main concepts. Now, how does the experiment come in? The experiment, I told you, only comes in modern science, and I'm going to explain to you now why the experiment can play a role once you have a concept of nature that's relational, where you're interested in relations, and once you have an idea of scientific knowledge that's only hypothetical. And when you put these two things together, then you get a role for the experiment. This is what I'm going to show you now. Now, the point first is that with the modern concept of nature and the modern epistemic ideals, universal relations of different degrees of universality, I'm not going into that, have to be generated and tested. You know, because you think nature is defined or organized in terms of natural laws. If I want to understand nature, explain nature, I must understand the natural laws, and therefore I must generate then and test these general relations, and they have the very general form whenever A, then B. And A and B are sets of variables or just one variable. So for instance, in the law of free fall, I give you the time, and then you can calculate from the time that the body falls, you can calculate what the path is, what the distance is. That's the relation, right, between time and path. So whenever you have a certain a certain time, then you can calculate what this distance is. All right. So mathematically, this is a function. This is just a function. B is a function of A, and A and B may be, but need not be, quantitative variables. Again, that's not that important. It's the functional dependence that becomes a role, or gets a role, because of the concept of nature that's relational, that says, well, nature is such connections between A's and B's. And by the way, you can, once you have this point, this is not the topic of today's talk, you understand why mathematics can enter modern physics, which is the case since Galileo. Physics is a quantitative science, it's a mathematized science, whereas Aristotelian physics was purely qualitative. So Aristotelian science is far from mathematics, it's very qualitative, so many of you possibly may love Aristotelian science more than modern science, but unfortunately it was not extremely successful. So you better switch to the more successful enterprise. All right, so this is why mathematics come in. But we don't want to see that. We want to see why the experiment becomes important for science. So if you are interested in these relations between B and A such that you can describe them as a function, you say B is a function of A, then the following happens. If the values of A, of this one, what is called the independent variable, can be practically realized, and the values of B can be measured, then the relation can be experimentally generated or tested. This is exactly what Galileo did. You know, he took his inclined plane in that fall, which is a proxy for the free fall, and then he said, okay, I measure the times, I look at it and look after 1 second, after 2 seconds, after 3 seconds, and then I measure the B, that is the distances, so I practically realize a fall of 1 second, of 2 seconds, of 3 seconds, and then I measure the other one, and once I do that, then I get the relation that I have measured, I have generated, or I have tested it, and this is the idea how to get at these relations that you want to produce. So if the experiment is reproducible, which means you can repeat it again and again with different values and so on, and if you then have the relation and you get the predicted values, namely, I wrote down the equation for free fall, if you get that again and again, then you say, okay, this is the confirmed relation, it's the law of free fall that we got out of these measurements. The important point is, you have to prepare something yourself. That's the intervention, the human intervention. You prepare the experiment such that you can generate the A's and then you measure the B's, right? And the generation includes the measurement here of the A's. So you've got to measure the times and you've got to measure the distances, but you generate that, and then you get out of this generation of the experiment, you get the relation you are interested in. So you may look then that relation is deduced from more general relations, then these more general relations are indirectly confirmed too, so there are more general laws of gravitation, and you can deduce the law of free fall from them, but that's a technical thing, that's not so important here. Now, what you have to see, and this is why I showed you the example, is this. The cognitive role of the experiment derives from the interplay of the modern concept of nature, which supplies relationality. You are interested in the relations in nature, and with the modern epistemic ideal for which hypothetical knowledge suffices. You know, it's hypothetical when you say the law of free fall holds for all cases, because you've only observed a very small number, right? Therefore, you cannot be sure that the law of free fall is universally valid. But you want to have that relation, but you have only a few data points, as scientists speak, so it's hypothetical. But you say that's good enough for science, we can't get more. In Aristotelian science, you would not have been satisfied at all. You wouldn't say, well, this is pure doxa, it's not episteme, you know, so it's uninteresting, it's not science. So, but people have calmed down a little. So what you see is then that the experiment together, or the experiment exploits the possibility that you're interested in relations and that you are satisfied with hypothetical knowledge. And therefore, the experiment comes into play for modern science. Now, how does that translate into technological exploitability? This was the idea. Remember the steps of the talk were concept of nature, epistemic ideal, leads to experiment. Experiment now makes understandable, intelligible why modern science is technologically exploitable. So we're going to look at technological exploitability. Now, I'm introducing only now that you have a certain law, such a function as I describe it, and that is experimentally confirmed. This is how scientists often speak, or inductively confirmed, that is such that you can trust it in the following sense, that the realization of certain values of A, this variable here, invariably produces the predicted value of B, namely this one that is predicted with that formula here, with that function f, under certain conditions. And if that formula, what the formula describes, is always the case when you measure it, so in the law of free fall, when you measure that, and then always the formula is satisfied with the values that you have measured, then you say, we have experimentally confirmed the law of the free fall. So this is the idea of experimental confirmation that you find in all of natural science today, wherever possible. It's not possible in astronomy, but in chemistry and biology, wherever you speak about that, you make experiments and look whether the relations that are postulated in that science are fulfilled or not. And if they are, you say, my experiment is, my law is, or my function here is experimentally confirmed. Now, the important thing is, and I hope this has become clear by now, is that a scientific experiment is usually done with the goal to explore or to generate the test or to test the relation f. You are interested in what is the law of free fall, and either you have an idea already and you test it, or you have no idea and you just play around. The idea is, I want to get at this function f that I wrote down. Distance is half times g times t squared. This is what you want to know. And what you do is, for that purpose, this is a fundamental scientific purpose for modern science, is you realize certain values of A, right, and look which values of B you get. Right? This is if you explore the function f, if you don't know what it is, or if you have an idea and want to test a certain function, then you realize certain values of A and look whether you get the predicted values of B. Right? This is just how you test, how you get and test the relation f you're interested in it. So you let roll the ball for different times, and then you look what the distances are, and then you check whether the relation is fulfilled or not. This is the idea of the modern experiment. Right? Now, the interesting thing is, once you have a relation that is experimentally confirmed, then you can carry out exactly the same physical action with another goal. So you do exactly the same, but for a different purpose, right? And I give you an example later. You realize certain values of A in order to produce certain values of B. And you know that the law licenses you to do that you can predict, if I do A, then I get B. This is because the law is confirmed. So you can do that, but this is precisely technical action. If you think what technical action is, it's doing A in order to produce B. This is technical action in the most general sense. You do A and you produce B. So if you want to start the engine of your car, for instance, you turn the key, at least in the older cars, and then the engine will start. And it's a complicated mechanism in between. That's technical action. Or you press the accelerator, and then the car will drive. Less than 50 in cities, I remind you. Anyway, so technical action is exactly that. And therefore, the relations you get from natural science by experiments are just the relations you need for technical action. This is not an accident. And I give you here a very obvious example. If you know a little, probably you know that clinical tests of a new drug that has a therapeutic application, they are tested in hospitals, right? You have double-blind and blah, 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 and randomized. That's all not important. But what you do is you give the chemical to patients, and then you want to find out whether it helps them, to put it very simply. So you try to find out, is there a relation between the application of that chemical and the health condition the individuals. And you're testing then the drug in that way. And the same exactly, once you know, yes, this is a helpful chemical, and you compare that with a therapy, you do exactly the same. You have the same sorts of patients, and you give them the pill. And in that case, if you are a doctor and want to use a therapy, you want to heal these patients or improve their health conditions. You do exactly the same physical action as you do in the experiment. In the case of the experiment, you want to find out, does this relation hold? And once you know that it holds, you can do exactly the same action as a technical action. Namely, you want to improve the health of the patient, and therefore you deliver the pill to them. So what you see is that every successful experiment that can be reproduced is at the same time a potential technical action. And that is the deep trick of modern science. Every experiment is a potential technical action. And this is, you see it very obviously in this case of experiments. And this is therefore at the heart of scientific knowledge, of modern science. Insofar as modern science proceeds experimentally, it's unavoidable consequence to produce technologically exploitable knowledge, because every successful experiment is a potential technical application. That's the basic issue. Okay. And one should also know that this is, of course, not only these simple things that Galileo did, but you can concatenate them, so you can put technical actions without human interventions in a row. So you produce, the human produces A, and then you know that by a law, B is produced, and then B produces C, you know another law, so you can make complicated machines, as it is the case. If you turn the key in your car, it's a complicated process. I mean, the kind of electrical blah, 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 and then it leads to the engine, and it's a lot of steps that happens there. And they all work in the same way. You are exploiting general relations, and you build a machine in such a way that this exploitation can be used. So that's the reason why you have up to now autonomous machines, which made all these law problems about responsibility. If something goes wrong, you know that with the self-driving cars, probably this is all something like that. This is the general structure, and it's built upon modern scientific knowledge that produces the relevant relations. And therefore, we can build machines. This is the trick on the basis of science, right? And in Aristotelian science, you cannot build machine on the basis of science. Technology was completely separated from science. Now, here's the conclusion. First of all, if you look, what is the core element in that transition from medieval science in the Aristotelian tradition to modern science? What is the key element? People very strongly disagree about that. Some say it's mathematization, others say it's experiment. And if you analyze all these elements, then it seems to me very clear that really the core concept, the deepest concept, is the concept of nature that plays the role. Namely, the relational concept of nature is the most basic and revolutionary element of modern science. That's the basis for everything else. Without that, nothing, you can never get to modern science. So it's this relational concept of nature. It's the step away from what is called essentialism, that you look at the essence of things, that you say, no, that's not available. We cannot really know the essences of things, but what we can know, at least hypothetically, is relations between things. And therefore, we should conceptualize nature as a system of relations, and therefore natural science tries to investigate the relations among things that we find in nature. So it's this relational concept of nature that's the core element. And that explains then the possibility of the use of mathematics in science, because only if you look at relations, you can mathematize. It's very difficult to mathematize essential qualities. I mean, some of them may be quantitative, but essential qualities are not by their nature quantitative. They may be really qualitative, and therefore you see that the use of mathematics naturally comes into modern science because you look at relations that you find in nature. Therefore, mathematics comes in, and then if you weaken the cognitive ideal that you say, I only accept of scientific knowledge, is that knowledge is absolutely certain. If you weaken that, And the point is, this is very hard, but people just gave up. They say, well, unfortunately, it's not possible for human beings to get proofs about natural phenomena. We may get that in mathematics, but not in natural science. This was a deep and bitter realization after 1,800 years of not really producing solid knowledge in the Aristotelian tradition. Then people said, okay, we have to give up this high ideal, and we've got to be a little more modest and saying, okay, hypothetical knowledge of natural relations, that's wonderful. And therefore, you get then a cognitive role for experiments in science, because you can experiment on nature because it's relations, and if you say the knowledge we get there is good enough if it's hypothetical knowledge, then you can say, I learned something scientific from experiments. And this is why experiments do play a role. And then once you've understood why experiments play a central role in modern science, you do understand why modern science is technologically exploitable, because every single successful experiment, meaning repeatable, confirmed experiment, is a potential action, and therefore modern science is a source of potential actions, and this is the technological exploitability of modern science, and I thank you very much.